We thank you for joining us this late afternoon. My name is Kiki Reyes, and I am the Media Relations Manager here at UC Santa Barbara. We are incredibly thrilled to announce our 7th and 8th Nobel Prizes, this time in physics. We will have a couple remarks before we can turn it over to Professor John Martinis. And without further ado, I am pleased to introduce UCSB's Executive Vice Chancellor and Provost, David Marshall.
We're not going to say which one of you is 7 and which one of you is 8. I'm here mostly to read some remarks from our new Chancellor, Chancellor Dennis Asanas. And this is a great welcome present for him after he's been here for about a month. I've already congratulated him on the quick results to have this fantastic news. So let me just read this from our Chancellor. I'm thrilled to congratulate our esteemed colleagues, UC Santa Barbara professors John Martinis and Michel Devoret, on winning this year's Nobel Prize in physics. We also extend our hearty congratulations to Professor John Clarke of UC Berkeley. This is a proud day for UC Santa Barbara and the entire UC community. I wish I could be there to celebrate with you in person. I'm in Oakland for the UC Council of Chancellors meeting. And he thanks me for sharing this statement on his behalf. The Chancellor continues, John and Michel, the impact of your work cannot be overstated. Your revolutionary work in quantum tunneling has been well known for over 3 decades. Your successful efforts to build an electronic circuit with superconductors in the late 1980s have had a transformational and lasting influence on today's technology, paving the way for components that we find in everyday devices, such as our cell phones, as well as for major advancements in communication, computing, and sensing. Your impact is limitless. As our campus's 7th and 8th Nobel laureates, you are part of a tremendous legacy here at UC Santa Barbara and a proud culture of interdisciplinary collaboration, innovation, and excellence that has been built over decades. Your prize-winning work is a testament to the critical importance of university research that impacts the lives of people, not only in California, but throughout the United States and the world. We join with our faculty, staff, students, alumni, trustees, colleagues, and friends around the world in celebrating your pioneering accomplishments and the deep honor and inspiration you bring to our university. Thank you. So those are the comments from Chancellor Asanas. I just want to add very briefly just a quick comment to say that this is an indication of why our research university is so important and why public support for our research university is so important. You know, George Washington in 1796 advocated for a public university, for a national university, because he argued for the expediency of establishing a national university, insisting that a flourishing state of the arts and sciences contributes to national prosperity. And he described publicly financed institutions as very cheap instruments of immense national benefits that serve to assist a spirit of discovery and improvement and to stimulate enterprise and experiment. And there's no knowing what accomplishments the discoveries that we're celebrating today will lead to. Chancellor Asanas mentioned a couple of the practical results. We've yet to see the real yield of the work, the research that our colleagues have done. And that's really what's so important about a research university, because it begins with discovery, with enterprise, with experiment, with curiosity, with a desire just to figure things out, to solve problems. And only years later do we see the tremendous transformation of society and the improvement of people's lives. But it's only by the investment in science that we ever get those results. And I'll just read you one other quick quote from one of my favorite figures in the University of California, Daniel Coit Gilman, who was the third president of the University of California, but he left the University of California to become the founding president of the Johns Hopkins University, which really was the first research university in the United States. And in his 1876 inaugural address, he said this, and some of the language is a little archaic and poetic, but I think you'll get the point. Gilman said, "Remote utility is quite as worthy to be thought of as immediate advantage. Those ventures are not always most sagacious that expect a return on the morrow. It sometimes pays to send our argosies across the seas to make investments with an eye to slow but sure returns. So it always is in the promotion of science." So this is an example of that investment where it may take decades, but in the end, you get more than a return on that investment. And I'll also mention that not only do we see the results of their research, but these are professors who have taught countless numbers of students, who then themselves go out in the world and teach other students and make more discoveries. So we're immensely proud of the contribution that our faculty, our colleagues have made, but also of what the research university has made as well. So thank you, and congratulations again to John and Michel. And we'll have a few other remarks from Dean Gable next.
Good afternoon. I'm Shelley Gable. I am the Susan and Bruce Wooster Dean of Science, and it's my privilege to welcome all of our guests to the University of California in Santa Barbara. Today is a historic day for our campus and for the Division of Mathematical Life and Physical Sciences, and especially our esteemed physics department. We celebrate two remarkable colleagues in the enduring power of science. We're here to honor a monumental achievement. The 2025 Nobel Prize in Physics has been awarded to two of our own faculty, Professor Emeritus John Martinis and Professor Michel Devoret. This is not just an award, it's a recognition of a fundamental shift in our understanding of the universe. Their visionary work revealed quantum physics in action on a scale large enough to see. This discovery laid the groundwork for the second quantum revolution, powering the technology in our lives today and fueling the quest for quantum computing of tomorrow. This work matters because it pushes the boundaries of what we know and what is possible. This achievement is also a reflection of a deliberate vision here at UC Santa Barbara to build world-leading hubs of scientific inquiry, including our quantum colony, which is unparalleled ecosystem for discovery, anchored by the nation's first NSF quantum foundry. Our culture of collaboration unites brilliant minds across departments, institutes, and campuses, building something far greater than the sum of its parts. The 2025 Nobel Prize in Physics is a testament to the vision of these two scientists. John Martinis has been a pillar of our physics department since 2004, and it was here that he led the team that first demonstrated quantum supremacy. And we were thrilled when Michel Devoret, a renowned physicist from Yale and a leader of Google Quantum AI, chose to join our faculty 2 years ago, further cementing our status as a global hub. They are now UCSB's 7th and 8th Nobel laureates, a legacy of leadership and excellence that inspires us all. So I want to thank David Marshall and Chancellor Sonis for their leadership and for joining us to celebrate this historic occasion. And I also want to acknowledge the incredible leadership of the chairs of our physics department, currently David Stewart, but also the past chairs, and also the amazing faculty that call UCSB Physics Department home. We are so proud to honor our two Nobel laureates today, and I am truly honored to introduce the 2025 Nobel Prize laureate, John Martinis, Dr. John Martinis.
Thank you very much for this press conference. As I was standing there, I realized I didn't have any prepared remarks for you. I'm not quite sure, haven't done this before. But I told myself I have to be really careful not to go into physics professor mode and drone on for an hour telling you some stories or whatever. But let me talk some of the interesting things. I really want to emphasize when we did these experiments, I was a graduate student with John Clarke at UC Berkeley. Michel Devoret was a postdoc. And this was a fantastic experience to be mentored by two wonderful people and great physicists. We all had our own unique, let's say, style and way we do things. But I learned so much from them that, throughout my whole career, I was kind of trying to recreate that spirit, that we had in there. I saw that. And, sometimes it was successful, sometimes not, but I knew, what it was like to have a really well-functioning physics lab where people are throwing ideas out and getting things to work right. So that was probably, in terms of my career, working with them was the most important thing in my career because I got that, basic idea on how to do science. I also want to mention something about UCSB, and at the time I was finishing up my degree, I came down to the ITP at the time, KITP, for a physics conference on the physics we were doing. But the last premier speaker was Richard Feynman talking about quantum computing, which had not really been talked about too much there. And it was an exciting talk for everyone. Frankly, I didn't understand everything. It was, maybe a little bit above what I was thinking at the time. But what I remember afterwards is everyone just kind of mobbed around him asking questions afterwards. And unfortunately, I was a poor, lowly graduate student, so I was on the outside ring of him where I could, barely hear what was going on. But I learned something very important from that, is one, this was a really interesting question and project to do, and that, physicists in general would be really interested in it. So very fortunately, at some point, the theory advanced and there was funding to start doing that. And it just was an exciting ride afterwards to really focus on this problem and try to do that. I want to build a quantum computer, and that was great. So I was able to follow that some when I was working at NIST in Boulder and really thank them for seeding that project and having the facilities to do it. I then came to UC Santa Barbara, which was very welcoming, wonderful people. Collaboration, yes, this is how we were. It's why I came here. If there weren't the facilities and collaboration here, I would not have thought that I could do it here. And then I had the opportunity at some point to go to Google and lead the hardware project there. And since then, I've left Google and started my own company. And our goal is really to build this quantum computer. Now, the problem is I'm retirement age. And if you look at, let's say, the number of qubits versus time, it's getting better. But if you extrapolate that out to 1 million qubits, I will certainly be dead by that time. And I'm going to say most of the people in here will be either retired or worse, okay? We have to speed it up. And it's been really great working with a big team of people and collaborating with the likes of Applied Materials, Synopsys, Hewlett-Packard Enterprise, another company, another semiconductor company we'll mention later this week, a bunch of startups, where we're going to use the semiconductor superpowers of the United States. We're fabricating very sophisticated devices, 300 millimeter wafers, to try to, to build this. We have a plan, we're going to do that. So I'm very excited. It's kind of my professional dream to do this. By the time I'm really too old to retire, I should retire now, but I'm not doing that. And that's great. So yeah, I'm very, very excited. It's a great honor. It's been a crazy day, but a fun day. And I very much appreciate what UC Santa Barbara did. And I appreciate that, UC Berkeley, the federal government helped support us, various funding, University of California, all these people working together to develop science is what made it possible. And now I'm a little bit more in the private sector. Maybe that's more appropriate at this point. But, it really was all this, basic research we did for decades that enabled this to happen and, enable us to have a vision on to build this thing. So hopefully in, not too many years in the future, we can talk about the useful quantum computer that we have built. And that's the goal for the future. Okay? I don't think I went on for an hour. That's good.
All right.
Do we have question and answer?
Myself off. Now we're going to do a question and answer. Let's start in the room. I don't know if I should walk over there.
I have bad hearing, so if you can repeat it, that would be good, or give the microphone. Okay, describe, yes, thank you. I've had this good question this morning from the reporters. So let me answer that. I went a little bit too fast there. Normally, we think about how atoms works and how molecules bind together. You have to describe that with quantum mechanics. And okay, you have to take advanced courses to understand how that works and get the math. But the physics of quantum mechanics describes that. Now, traditionally, and I still hear it often, quantum mechanics is the physics of small things like atoms. But what we showed is that it's a much more general and applicable theory well beyond how atoms works and other systems work. And in fact, the devices we make, you could hold in your hand. It's maybe about this big. You can see the device with your hand. And that device, which is big, has many billions of atoms, obeys quantum mechanics. And very specifically, it's the current and voltages of this electrical circuit that obeys quantum mechanics, kind of in the very analogous way how you describe how the electron's moving around the atom. So this is something we call macroscopic quantum mechanics. And it really opens up a whole new field where people can build these devices, in the lab, in the clean room at UCSB like we did here, and then operate them at low temperature and see the quantum mechanics effect. So you can build atoms that are totally different than any quantum system you're going to see in nature. And that's what's kind of exciting. That's what drew me to it at the time. But of course, what's been interesting is since you're building an electrical circuit atom, if you want to build a quantum computer, which, all our computers here are made out of electrical circuits, then it's kind of a natural mapping to, think about building a quantum computer out of that. Now, there are pros and cons, and there's, decades worth of research to get there. But, you fundamentally have an idea that you can do that. And I'd like to say, when I was here at UC Santa Barbara, I was working with Andrew Cleland, and he was making quantum systems out of little cantilevers of metal and insulator. Again, it's the mechanical movement of a system, and again, that can be described by quantum mechanics. So it's really opened up a whole new field of ways to look at quantum mechanics in new and novel ways. Yes.
Just how are you feeling? I mean, you woke up today and you get to find that your life's work is being recognized. Yeah, of course.
So,
just how are you feeling?
How I feel? Well, fortunately, I'll tell you the story. It's a funny story. What happened this morning? Okay, so I went to sleep very soundly last night, and but my wife was reading a really nice novel, so she stayed up till 3 o'clock reading her novel. And then all of a sudden the phone started ringing. And, she answered it eventually and, found out reporters and what was going on. So She could have woken me up right away. In this case, I would have answered differently. Okay, but she let me sleep in till 5:30. Okay, because she knows that I need my sleep. So then, you know, she woke me up, and I looked on the internet, and oh my God, this has happened. And then at 6 o'clock, I had an interview with some reporters who had driven to my house and wanted to get a fresh interview. I think they wanted to tell me in bed, but my wife, you know, wisely said, no, let's not do that. And it's just been, you know, constant phone calls and emails, and you know, people have been really great with their emails and congratulations. I was telling people in the hall that I think the most special thing is to hear from old students how they took a class and they liked the class and congratulated me, and that's been really nice. So it's an amazing day.
Anyone else with a question?
How will you celebrate with your wife?
How will you celebrate with your wife?
One of the CEO of my company is driving up from LA, and we're going to go out to dinner tonight. Yeah, it's you know, when you start a company, I'm really too busy. It's like being the associate professor, where you always are trying to do something. So you know, I'm really busy and I have a lot of things to do. But yeah, we'll go out and celebrate tonight. Yes.
Sonia, go ahead.
Hi. Two-part question, actually. So you were a grad student at the time you conducted this experiment you're referencing here. And I'd like to know what led you to the experiment. So what were you trying to answer? What were your fascinating about?
Thank you. Yeah, I could have given my 1 hour answer and covered that, but thank you for the question. What had happened at the time is Anthony Leggett, who's a Nobel Prize winner, had been proposing at the time that, you know, maybe kind of the question, like Schrodinger cat, what's going on there, maybe quantum mechanics doesn't work at the macro scale. And that maybe could be, you know, part of it. And that, in fact, no one had tested it before. So we thought that that would be a very good way to test it, using these superconductors like we did. Now, at the time, there had been some experiments to, you know, do this, but they weren't very complete and convincing. They had some data, but it was not. But in hearing all this, I had, you know, told my advisor, John Clarke, this is really interesting. Can we do something here? And John, of course, being very experienced, you know, he said, well, that's right, you know, it's interesting, but what are we going to do new? What are we going to do better than everything else? And the interesting thing that we did is we figured out that we could measure the parameters more accurately, very accurately, than what had been done before. So it's just a matter of good experimental design. And in fact, the key idea here was that these were actually microwave circuits. And up until then, no one had thought that way. As the microwave circuits, it's going to resonate back and forth. And because of that oscillation, it's just like with atoms, instead of the electron spiraling in, it actually jumps in there with discrete energy levels. And then we, you know, eventually decided, yeah, we could see that and it would be very interesting. So, you know, it was something that I had wanted to do, but it's only with John Clarke and Michel Devoret that we figured out, sorry, it's a phone call. It's happening all day. You know, it was only because of working together, we kind of decided what we wanted to do, and then we decided, you know, how we would do it. And it just took a few months as we were experimenting it to really get to the heart of all the things you had to do to, you know, to get it to work. Very much a collaborative experience.
When you got your result, did you have a sense of the magnitude of your discovery? Like, what was going on in your mind?
So there's a funny thing that I visually imagine. When we did these experiments, we had an oscilloscope, and there was some trace on it that talked about when the junction switched. But I vividly remember at one point, seeing this trace and then seeing 3 dots on the trace. And those dots are the spectroscopy resonances that you see with that. And I knew, without even analyzing the data, just the raw data, that this was going to be extremely convincing to people, because classically it's kind of like just a smush of a line. But when you see, 3 little dots there, then you're really seeing the quantum mechanics. So at the time it was great, and we wrote the paper, whatever. We thought it was pretty exciting and pretty new, but it was good for the time. But I think it's only because of the tremendous amount of work that has been done to build a quantum computer and use this physics over the many decades that the importance of this really came to light. At the time it was a nice experiment, it was very well covered. And I think a fundamental experiment that's not, you can't do that all the time. But it's really the work of many, many people around the world that made this as important as it is now. And I would say I'm very proud that I think there may be thousands of physicists who are employed trying to build a quantum computer. And I'm happy to be part of giving all these young people nice paying jobs and doing some interesting science at the same time.
Any other questions? Any last?
Yeah, actually, I have a related question to what you just said. I'm curious if you have thoughts about the role of public-private partnerships in advancing quantum computing, especially when it comes to solving really complex problems like new drug discovery and new materials.
Yeah. So the name of our startup company is called Colab, QOLAB, which is Q, of course, plus collaboration. And the point of our company is we're collaborating with really advanced semiconductor manufacturers like Applied Materials and alike, but we're also collaborating with other startup companies, but we're also collaborating with lots of groups in academia. University of Wisconsin, we're setting up something here at UC Santa Barbara with a new professor in engineering, because we think there's lots of ideas out there and we need to be collaborating very closely with them to make this happen. Now, when I was at Google, they tended to want to, have a lot of money and to hire people and do it all inside, and that's okay. But I think this collaborative model is going to be more, more fruitful, because we really get a lot of interesting ideas. But we have a lot to catch up to. So yeah. But it's a very good atmosphere to invent things. And I'm very proud of our collaboration team solving problems. They've been fantastic.
I don't see any other questions in the audience. Anything that you guys want to ask before we wrap up?
Oh, let me ask another one then. We're gonna wrap up.
Please.
Please. Oh, so you with your team, your UCSB/Google A quantum team, actually built an early processor, superconducting processor. What would it take to make a practicable quantum computer?
Yeah, okay. So when we built it at UC Santa Barbara, we built it with the clean room here, which is very good. And then when I was at Google, we were using the UC Santa Barbara facilities to build it also. And we were able to get up to 53 qubits. Doing that, facilities here are wonderful, and it's great, and we were able to move very quickly and do that. Google has since, after I left Google has since built their own facility and the like, and they're using 200 millimeter wafers. Our thesis, and that's what we're raising our money on and doing it, is that this kind of academic style processing that we do here and even Google is doing and everyone else is doing is not going to be good enough. And for those who know about processing, it's using something called liftoff, which is evaporating metal through a photoresist stencil, okay? Which is, I would say, 1950s, 1960s technology. No one does that anymore. So that's why we're going to the advanced manufacturers to do what's a deposition and etch process, but using very sophisticated tools to build the new processes. And it's taken money and time to get it up going, but things are going very well. And once they get things to work, kind of out of the box, they can build things that would just blow your mind away trying to do it in an academic thing. And that's what we are hypothesizing that we need to do to get this to work. And like I said, you know, if I want to get this work in the next 10, 15 years, okay, this is what we're going to have to do to get it. So that's very exciting. And, you know, okay, experimentalists like to, you know, use expensive tools and build things, whatever. So when we work with someone like Applied Materials, you know, we can use, you know, $50 or $100 million deposition system, which we could never afford, and then use a several $billion clean room, you know, use some of the facilities in that to make it. And as an experimentalist, it's really fun to, you know, kind of work with them and figure out, you know, what's the right way to put all this together to build it extremely precisely. And I think it's really kind of interesting to think about using this very sophisticated manufacturing in the United States, because the United States does have, you know, the capability to do that. Maybe making semiconductors cheaply, other countries can do, but to make them really well, that's something we have a lot of, you know, technology to do that. And it's kind of fun to, you know, try to push that forward.
Anything you would like to add?
Just thank you for being here. It's a really a great honor, and I love all your questions and talking about this. It's been something I've done my whole career. Okay, and you know, people may not know, but when people do their PhD experiment, they usually move off to other things, but they tend to come back to their PhD experiment because it has good memories for them, hopefully. And it's been a real pleasure to, you know, just keep building on something that we thought about very carefully back in the mid-1980s, and keep working on that and building it better and better. And that's been, and understanding the physics better and better, because there's a lot of subtle things going on. That's been a great pleasure.
Okay. This concludes our press conference, and thank you guys for attending. And congratulations, Professor Martinis. And yeah, if you guys have any other things to add.
If you're shy, please come up.
Yeah, you can come after and talk to him. I'm sure he'd love to talk to you.
Thank you.
All right, thank you guys.